right, my name is Chris Ford. I am a earth science major, I guess. And so, kind of break the nerves off, I'll start with a joke. So, a baby kangaroo is known as a joey. So, what do you call a lazy joey? A pouch potato. Ha ha, quite funny. All right, so being here, we have various faculty and students. So, who teaches or is part of a general education course, or has been? Right, most people. Okay, and so how many people have taken an earth science general education course? I've taken several. All right. So mine is all about that. In those classes, we talk about all different types of weather phenomenon that go on. And one of those things is El Nino and La Nina, or some people refer to it El Nino and the Southern Oscillation, ENSO. So that's what that title is up on the top there. So I'll give you kind of a brief overview of what El Nino and La Nina are. So this is a phenomenon that happens rarely, well, not quite rarely, but every 2 to 7 years is how often it reoccurs. That's how it starts is up in the Pacific Ocean, the South Pacific Ocean. That's Australia, the U.S., and Peru right there. So the ocean and the air normally circulate in a specific pattern, and that's what keeps Earth going kind of normally. What happens during an El Nino year is, for whatever reason, that circulation stops. Sometimes it even goes a little bit backwards slowly. And so that causes the ocean here to heat up a lot. And it kills fish in Peru, so the Peruvians don't get their fish. It causes some problems there. And there's more rain here and less rain up in Asia. So it changes things, especially regionally, but also globally for the world. And so we always talked about that and how it affects the U.S. in class. And over here on these other maps, we'll talk about those in a minute. But you can see California, Nevada, Utah, and the Pacific Northwest. So I always talk about how during an El Nino year, when all that water's heated up, that things kind of switch around. And in the Southwest and California and Arizona, they uncharacteristically get a bunch of rain. And in the Pacific Northwest, where it's rainy and dreary, it's really dry and they don't get rain. So it causes this weird shift in weather. And El Nino that's when it's really warm. But La Nina is the inverse, where that's really cold water and circulating maybe quicker than normal. And so there's two kind of different things that happen, and they both affect the weather quite drastically. And so you can imagine what the La Nina would do. And La Nina and El Nino are Spanish terms. El Nino means the boy and La Nina means the girl. And that was coined because of the Peruvians. That's where the name came from. But so during La Nina, the cold water cycle, we get these more enhanced extremes. So in the Pacific Northwest, we'll get a lot more rain than normal, and then the Southwest, we get even less rain than normal, and it's a lot drier than normal. They always said that here in Utah, we're kind of in this no man's land, kind of in the middle of that either way. We get a little bit we get affected a little bit, but not quite a lot. It's always what my teachers said. And so I was kind of interested in that because it kept recurring in all these different science classes that I was taking. And so I wanted to look at and see what are the effects. Is there any real effects on Salt Lake or the Central Wasatch Mountains? And my idea with the El Nino would have a bigger effect on the Wasatch Range, and that we, maybe get more snow, get involved in some of that craziness of weather that we see. And so I developed this project to kind of look at that and see if we had any strange weather because of this phenomenon. I don't know, and a lot of people here like to snow and ski, and so I figured that would hold some tracking for people's interest. So essentially, I used the National Ocean Atmospheric Administration. It's a government administration, and they tracked all kinds of this stuff. And so they use this sensor area. It's Nino 3.4 is what they call it. And so if they have unusually high or low water temperatures in that area for 3 months at a time, they deem it an El Nino or La Nina effect. And that's what this little graph over here is. This is list back into the 80s of all the El Nino years and La Nina years down below this median line. And so I used all of those to determine which were El Nino years, which were La Nina years, which were neutral years where there was neither case, so I could compare all three of them. And I used only extreme or moderate cases so we could get kind of a more stark contrast in these graphs that I'll talk about a little bit later. I used that to determine it, and then I used 4 snow telemetry sites in the central Wasatch Range. Down here there's one at Snowbird, Brighton, one in Park City called Thanes Canyon, and then one in Mill Creek Canyon. So these 4 stations in the central Wasatch, and I looked at the water year for all the years that we looked at and determined snow water equivalent, so how wet and heavy the snow was that we got in those years, and also the air temperature that we got in those years at those 4 stations. So after we compiled all the data and compared and contrasted them, these are the graphs that we came up with. These are the snow graphs, and so the blue is the La Nina year where the water is colder, and then the red is the El Nino year where the water is warmer and going sometimes counter to what it should be doing, and then the gray is the normal. So as you can see, in all 4 of these snow graphs, we get more snow water equivalent, a lot wetter snow during the La Nina years, especially at Snowbird. That I had to double check that and recheck that several times to see if that gap was correct, because that is 20 more inches of snow water equivalent at Snowbird during La Nina years. And it's happened to all of these ones that La Nina was higher and the El Nino was lower, that we got less snow. And it kind of correlates with some of the air temperature graphs as well. Those graphs are kind of hard to read, they're a little bit jumbled, but there is a trend amongst them all. And essentially what you get is during a La Nina year where the water is cold, and doing that, we have a warmer fall, a warmer autumn, but a colder winter and spring than normal. And then in an El Nino year, where the water is warm and going counter, we have a colder than average fall, but then a warmer than average winter. And then the spring is also cold. So some of that correlates into some of these fancy maps that I got over here as well. Another thing that we looked at in my class was the jet stream. This is a new thing we're introducing to the project, that the jet stream is this big band of wind in the upper atmosphere that controls and moves a lot of clouds and moisture and weather, and it always comes in into the U.S. off the coast of the Pacific, sometimes from Canada and Alaska. It's bringing all of that water and moisture over the land. And so what we looked at was the geopotential height at 700 millibars. And essentially what that tells us is just where that jet stream is normally. And we made these maps up because they show, they're anomaly maps. They show where the jet stream is during a La Nina year and an El Nino year, as opposed to what's out of normal. So the darker purple shows where that jet stream is out of character, what's different about those years. So the one on the right is the El Nino years. So when we get all that crazy weather down south and we get warmer winters up here, and that is because the darker purple is that jet stream that dips way down below where it normally goes, and so it's pushing all of that moisture over the Pacific Ocean and all that cold weather down in California and Arizona and New Mexico, that area. So that's why they get a lot more snow and rain and crazy mudslides because of all of that. And then in the La Nina years, the cold water years, the purple is up here in the Pacific Northwest, so it's pushing all of that inland to the Pacific Northwest. And you do see that Utah is technically in the white in the normal area, but with all of that getting pushed in up there, it shoots off and hits us a little bit more. There's more chance, whereas in an El Nino year, all the weather is getting pushed down there into California and New Mexico. So we kind of miss out on some of that, and that's why we have the warmer springtime, or the warmer Januaries during an El Nino year, and the colder winters and springs during a La Nina year. So those are kind of the observations that we got from all the data, but what does that mean? What am I just rambling on about? So we can use this to determine several different things. So if we know that a La Nina year is coming, we can prep by hiring more snowplows, have them more on ready. You know, it means a lot of things for a winter-based Utah economy that is heavily reliant on tourism and winter sports. You know, we could even maybe use El Nino to try and get the Olympics back in Salt Lake. Whereas opposed to a La Nina year, we would know that we would need to restrict water flow and conserve our water reservoirs so that we don't run out of water in those warmer, drier summers after those warmer, drier winters. So those are some of the human factors that we have and why we're interested in this. So. And that is all of the human factors I could think of. There's undoubtedly more. Is there any questions about any of this that I've presented from anyone?
Has there been any trend indicating more frequent or more extreme fluctuations in this pattern as we move forward that would be indicative of like the
Yeah, there's definitely some trends. And some people fight climate change because they say 1997, the weather's been cooling down since then, but that was actually a strong El Nino event where things were really warm. But you do see, looking at this graph and also kind of studying it, there is an increase of El Nino years kind of coming up, so these more extreme cases. And with those warmer global environments, we also get an increase of natural disasters such as hurricanes and mid-latitude cyclones and all of that kind of stuff. So, but there is definitely a rise, especially in the last decade or so, 2 decades since 2000, especially in this last few years. There's been a few cases of it occurring more often than we've normally seen. 2015 was a big one. 2016 continued in that trend. Not quite as strong though. Does that answer your question? Okay. Any others? You know, I'm not sure if NOAA, the National Ocean Atmospheric Administration, has anything in place. I do know that they monitor this quite heavily, and so that they can gauge that. It kind of is just dependent on ocean temperatures, but so I think it would be somewhat difficult to predict 10 years in advance, but I'm sure that they are working towards that because it is a big focus at NOAA. So I don't quite know. That would be interesting though, something worth studying further. Yeah. Yeah, in the northern hemisphere. Yeah. So things kind of get backwards up here in the southern hemisphere, which affects essentially how everything else is going on. And the northern hemisphere gets a lot colder because of the circulation doesn't quite work normally, because this one's circulating as well. And so it affects the circulation with its neighboring rotational cell that comes down this way actually. And so it gets a lot colder, and so the oceans don't circulate quite as well up here as well. So that's why the jet stream dips lower, is because of that colder air allows it to get lower into Mexico and California. Thank you so much.